So now we're in a position to finally answer the question that we started off with, right? I've got this graph here. This is the graph of f of x equals 4.9 x squared. That's the distance an object has fallen after x seconds. And the way we're going to kind of start this final exploration here, I want to talk about the slope of the tangent line, and we'll transition this into the velocities and the rates of change near the end. So what we're doing, I'm trying to find the slope of the tangent line at x equals 1. And you remember we ran into some trouble with this because to find the slope we need 2 points, not just one. So what we did is we said, okay, look, I'm going to look at secant lines. Right, and as I let this point down here, I'm going to keep that point here at 1 comma f of 1 fixed, and I'm going to let this point down here kind of slide closer and closer to 1, right? And as this point gets closer to 1, these secant lines get closer and closer to the tangent line, which means their slopes get closer and closer. Remember, this whole idea of getting really close to is what our limit lets us talk about. Okay, so I want to talk about the slope of the secant lines. Well, what is the slope of a secant line? Well, if I take just a random one of these down here, the coordinates of this point are x comma f of x, which means the slope of the secant line is f of x minus f of 1, that's the difference of the y values, divided by x minus 1. And what I want to know is what is the slope as x gets really, really close to 1. Remember how we say that. I'm going to use my limit. The limit as x approaches 1 of f of x minus f of 1 over x minus 1. And this is going to be the slope of the tangent line at that 1 point. Okay, so what is this? We can calculate this now. Right, f of x, let's keep the limit as x approaches 1. F of x is 4.9 x squared. F of 1 is 4.9 over x minus 1. And so let's see, I'm going to use my limit rules. I'm going to factor 4.9 out of the numerator and then bring that out in front. So this is 4.9 times the limit as x approaches 1 of x squared minus 1 over x minus 1. Now, if you try to just put 1 in, which is a reasonable thing to do, this is the limit of a rational expression. If we just put 1 in there, we get 1 squared minus 1 over 1 minus 1, and that's 0 over 0. And we've seen many examples now. Sometimes we can fix this, right? I'm going to factor the numerator. This is 4.9 limit x approaches 1, x plus 1, x minus 1 over x minus 1. And just like we've seen happen many times, these x minus 1s cancel. This is 4.9 times the limit as x approaches 1 of x plus 1. X plus 1 is just a polynomial. To find the limit, we put x, we replace the x with 1. This turns into 4.9 times 2, which is 9.8. And if you watch the previous lecture, if you look back in your notes or whatever, you'll see that when we try to do this by looking at points and making a table and looking at the trend of the slopes of the secant lines, that's exactly the number that we were approaching. Okay, so now what have we done? We have a method, right? And I want to generalize this a little bit. We have a method for finding the slope of a tangent line. And I want to generalize this. So here we've got our definition, right, of the slope of the tangent line, we've got a name for it, right? I'm going to call this the derivative of the function at a. And there's the generalization part. Instead of talking about a specific number like 1, right, I'm going to generalize this to a. And if you look at my limit over here and compare it to what we did on the last slide, you see I just replaced all the 1's with a's. Okay, so now we've got some language here, right? The way we read this symbol, and you notice I've got that little apostrophe kind of added in there. The way we read that is f prime of a. And what this is saying is if a is a value in the domain of f, right? So we can't talk about the derivative at points where the function isn't defined. And f prime of a exists, specifically this limit exists, then we say that f is differentiable at a. And the process of actually doing the calculations is called differentiation. Okay, so this is going to be our definition. This is a key definition. We're going to be working with this a lot throughout the rest of this chapter. But there is another version of this definition, right? And it's sometimes more useful to think of it this way, right? But they are going to be equivalent. So I'm going to start off with kind of the same situation. I want to find the slope of the tangent line at x equals 1. So this is the point, still 1 comma f of 1. And now I've got a second point up here. And this time, instead of talking about x comma f of x, I want to talk about this other point in terms of this distance, right? This distance h. All right, well, if that distance is h, then this point here is x plus h, which means these coordinates are x plus h, comma, f of x plus h. And now I'm going to go the same way. I'm going to say, what's the slope of the secant line? The slope of the secant line is f of x, excuse me, we're doing this with 1, right? This shouldn't be x plus h. This should be 1 plus h and 1 plus h. So it's going to be f of 1 plus h minus f of 1 over 1 plus h minus 1. And I'm going to clean that denominator cleans up a little bit. This is f of 1 plus h minus f of 1 over h. Now, to get to the tangent line, I'm going to take a limit again, just like I did before. Only now, what I want to do is I want to let h get really small, because as h gets smaller and smaller, closer and closer to 0, the 2 points get closer and closer together. So I'm going to do the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. And if you evaluate that limit, I'll actually leave that to you for practice. If you evaluate that limit, you should end up still at 9.8. So it's two different methods, two different formulas for doing the same thing. All right, and what I've done here, I've done the same generalization. Instead of doing this f prime of 1, I've replaced the 1 with a, right? And then we get another general formula, right? Two different ways of defining the limit. They both will get you the same answers. Which one you use, that's always a question when we get asked, right? Which formula should I use and when? It's a little bit trial and error. You're often going to have to do some kind of unusual factoring if you use the x approaches a, the original version. I usually start off with this one and see what happens. If it starts to get a little uncomfortably messy, maybe I'll switch over and give the other one a try and see if that works better. Okay, so now we can talk about our actual velocity. Okay, so here's what I want to do. I want to talk about rates of change now, because that's what velocity is, right? It's the rate of change of the distance traveled. how do we define rate of change? Well, rate of change, the average rate of change, right, which is all we know how to do so far. The average rate of change is the change in the y values divided by the change in the x values. Okay, but what is this? Again, now let's see if we can't be general. Instead of talking about 1, let's talk about x equals a. So this is a comma f of a, and this other point here is x comma f of x. So the rate of change is f of x minus f of a divided by x minus a. And if I want to get the instantaneous rate of change, the rate of change at a, right, I'm going to do the exact same thing we've been doing. Let this x value get really close to a, and that will give me what's called the instantaneous rate of change. That would be the limit as x approaches a, f of x minus f of a over x minus a, but we've seen that, right? That is exactly our definition of f prime of a, the derivative at a. Okay, and the instantaneous rate of change, that was what I wanted. This rate of change, this average rate of change, this is the average velocity if we're doing distances and times, which means this instantaneous rate of change is the instantaneous velocity. In other words, it is the velocity at that one individual point in time, and that answers our question. That answers Newton's question, right? The question that was being thought about way back in Newton's period. So we talked about a number of concepts here, and all of these concepts are equivalent, right? We've seen we have our new concept, f prime of a, and that we saw was equal to this limit, and it was also equal to this limit. Well, the language here, this f prime of a, this is the math concept, this is the derivative. This second limit here, this was the geometry interpretation. This was the slope of the, let me write this below, slope of the tangent line. And this this third part, this second limit, this was the instantaneous rate of change. Okay, so if you're working on a problem, you're trying to answer a question, and you see it talks about what is the instantaneous rate of change of this function. In your head, instantaneous rate of change automatically should translate to the derivative. And the derivative is something that you're going to know how to find. We're going to spend a lot of the rest of the class talking about specific ways of finding the derivative of a given function. Okay, so what's next? Now we've got this new concept, this new definition. What we're going to do in the next lecture in the series, we're going to look at a whole bunch of examples, right? See how we can use these definitions to actually calculate the derivative of various functions at various points.